class number 3. We're going to move on to chapter 6. So things that are coming up are highlighted in orange. Project 1 is due next class. Okay, project 1 is due Wednesday. The Oronico Flow project. It's posted in Moodle if you didn't get one. I have a couple other extra printouts. If you don't have one, just ask me after class. And then Wednesday, I'll give you quiz 1 as a take-home, and it'll be due Friday. Okay, so today we're going to introduce antiderivatives, and we're going to revisit from last class how to create values of a function using the fundamental theorem of calculus part 1. We're going to draw some graphs of functions based on the graphs of their derivatives. Okay, can somebody find an antiderivative of 2x plus 3? Some function whose derivative is 2x plus 3. X squared plus 3x. Can somebody give me another antiderivative, another function whose derivative is 2x plus 3? Yes. You can always throw a constant on the end because its derivative is 0. So the general antiderivative of 2x plus 3 is what's known as a family of functions, x squared plus 3x plus c, where c is an arbitrary constant. Could be anything. Okay, so let's review the relationships between a function and its first and second derivatives. So these are sort of like a big time summary of the stuff that we learned in Calc 1. Okay. When f prime is positive, that tells you that f is increasing. When f prime is negative, that tells you that f, right, its antiderivative, is decreasing. When f is concave up, that tells you that the second derivative is positive. It also tells you that f prime is increasing, right? Because I'm using this relationship from here. Just instead of f prime and f, it's f double prime and f prime. They have the same relationship to each other. All right, and then when f is concave down, that tells us that the second derivative is negative and that the first derivative is decreasing. Okay, so this is like super, super, super important. Okay. So we want to work backwards from f prime to f. We're just going to apply what we already know in a different way. Okay, so this is all information we already know, but we're just going backwards from f prime to f instead of f to f prime. So I'm going to sketch a function given a graph of its derivative. So here's a derivative function. This is f prime. And I'm going to sketch its antiderivative. All right. So from 0 to pi, okay, this is f prime. It's positive, right? It's above the x-axis. F prime is positive. So what does that tell you about f? When f prime is positive, f has to be increasing. Okay, so I'm just going to write some notes here. From here to here, from 0 to pi, f has to be increasing. All right, so but from 0 to pi over 2, from 0 to pi over 2, f prime is increasing. Okay, what do you know about f if f prime is increasing? Go back and look at your summary if you want. Yes, f prime increasing tells you that f is concave up. Okay. So we know from 0 to pi over 2, f is concave up. And then f prime is decreasing from pi over 2 to pi. Okay, so from pi over 2 to pi, f prime is decreasing. That tells you that f is what? Concave down. Okay, so then I'm concave down on the rest of the interval to pi. So when I try to sketch my antiderivative, From 0 to pi, I have to be increasing all the time, but half of it is concave up, and then the rest is concave down. Okay. All right, where do I start? What's my value of f at 0? You're all staring at me blankly because I didn't tell you, right? There are infinite antiderivatives. They all differ by a constant, which is a vertical shift, right? So wherever I start, it doesn't really matter. I just have to follow the shape, and I'm going to get one of the antiderivatives. Okay. Sometimes they'll tell you where to start, but I didn't in this case, so I'm just going to start at -1. You'll see why in a minute. Okay, up until pi, which is at about 3, right? I have to be always increasing, concave up, and then concave down. So let's see, I'm going to put pi in here. And then pi over 2, it's like right here-ish. Okay, so always increasing, concave up for half of it, and then concave down for the rest of the interval. So it's always going up, but it's concave up and then concave down. All right, let's analyze the second piece of the graph over here. From here, pi over 2 until, sorry, from pi until 2 pi, my derivative function is negative. It's below the x-axis. What does that tell you about f? If f prime is negative, f has to be decreasing. Okay, so on this whole interval, we have f is decreasing. Okay. All right, and now this is f prime. Okay. From pi to 3 pi over 2, f prime is decreasing. It's going down, right? When f prime is decreasing, what does that tell you about f? Concave down. Okay. So f is concave down on the first half of this interval. And then f prime increases. F prime is now going up. F prime is increasing, which means that f is concave up. Okay. So when I draw the second piece of this graph, it has to be always decreasing, but it starts concave down and then it finishes concave up. So let's mark, here's 2 pi, halfway between these two, 3 pi over 2. Okay, so I've got concave down, decreasing, still decreasing, but switches to concave up. All right, so this is a graph of f of x. So let's see if we can confirm this analytically. This first function, the derivative function, what does it look like? It looks like a graph of sine x, right? This looks like y equals sine x. Okay, and then this function that I just drew here, it should be the antiderivative of sine x, a function whose derivative is sine. So what? Negative cosine, yeah. And that is the graph of negative cosine x that we drew. All right, now I could have started somewhere else. I could have started my function at 0, which is pretty common if they don't give you a starting spot. And my function would just be a vertical shift up. It would be the exact same shape, like this. Should have finished at 0. Like that. And this would have been y equals negative cosine x plus 1. Because any two antiderivatives have to differ by a constant, right? So antiderivatives are always vertical shifts of each other. All right, so to be able to draw antiderivatives based on an f prime function, this is what you need to refer to. Okay. Memorize it or write it down. That's what you need. Okay, so just like last class, the fundamental theorem of calculus part 1 can let us actually calculate values of an antiderivative from the original graph if we're able to find the integral by looking at areas. So here's a graph of f prime from -4 to 4. The function consists of 2 lines and a semicircle, and I'm telling you that f of -4 is 1. Okay, so this is what I did not give you in the last one. I didn't give you one starting point. Now I'm giving you one. F of -4 is 1. So you can fill that in right away. We're going to figure out f of 2. Okay, and then we'll finish the rest of the table. But I want to do f of 2 first. And I'm going to do it using the fundamental theorem of calculus. So the fundamental theorem says that I would like to know f of 2. Okay? I want to know f of 2. I know something about f of -4. So I'm going to use -4 and 2 as my 2 important x values. And the fundamental theorem says that if I integrate from -4 to 2, the 2 x values, one I know and one I'm interested in, integrate the derivative from -4 to 2, that should equal f of 2 minus f of -4. That's what the fundamental theorem of calculus part 1 says. That's how. So there are 2 ways to calculate the area under a curve. You can do it directly using area, look at the graph, calculate areas, or you can try to do it analytically if you can find an antiderivative. Okay, so the integral from -4 to 2 of f prime of x dx. That means find the area under the curve from -4 to 2. So see if we can do this. It's the area between the curve and the x-axis. So I've got the x-axis and the curve, area between them, x-axis, curve, area between them, and I'm looking to go up until 2, from -4 to 2. All right, so I have to calculate the area here, remembering that area that lies below the x-axis is negative. And these are all just triangles and pieces of circles, so I can calculate them using formulas I know from geometry. So this triangle is 1 by 2, 1/2 times 1 times 2 is 1. It's below the x-axis, so it's got an area that's -1. Area, in quotes, counts as negative because it's below the x-axis. All right, this triangle is 3 by 2. 2 is 6, so its total area is 3. Right? Okay. And then I have a quarter of a circle here. That circle has radius 2, and the area of a circle is pi r squared. So this whole circle would be 4 pi. It's just a quarter of the circle, so its area is pi. Good. All right, so my integral is just the sum, the net sum of the areas where you count area below the x-axis as negative. So I've got 2 plus pi as my integral from -4 to 2. F of 2 is what I'm looking for. I don't know it yet. And f of -4 was given as 1. Solve for f of 2 just by adding 1 to both sides. So I get f of 2 is 3 plus pi. So I can put that here, 3 plus pi. So you could fill in the table integer by integer, right? Or you can use the fundamental theorem to get any particular x value you want. If I was going to go integer by integer, I would just look at areas over unit intervals, right? So from -4 to -3, the area under the curve is -1. That's how much your function value changes by. So it was 1, it changes by -1, so now it's 0. Then we do the next interval from -3. I'm trying to figure out from -3 to -2. How much does my function change by? And that is the area under the curve. So I look at the area between the x-axis and the curve, and that is +1. So then I add 1 back here. Next unit interval. I want to know how much the function changes from -2 to -1. So from -2 to -1, I find the area under the curve, which is 1.5. So I add 1.5 to my previous value, and I get 2.5. From -1 to 0, the change of value in the function f is the area under the f prime curve. So I find this area, and it is 1/2. Add a half here, and I get 3. My next unit interval is hard, but I don't need it. I'm going from 0 to 2 for my next one, right? 0 to 2 is a quarter of a circle. It's got area pi. So from my previous value of 3, I add pi to it, and I get 3 plus pi. And then I add another pi. So I get 3 plus 2 pi. Yes. What about it? How what came about? F of -4 was given. It's 1. Yeah. Yeah, I just replaced f of -4 with its given value. Questions? All right, that's it for the lecture part. You can get started on your activities. Don't forget the answers always follow the activities, and then there's even more practice/challenge problems. And if you even finish those, you have a project due next class that you could work on.